Hello and welcome to another one of our videos in our series of videos on trigonometric identities. Today we're going to talk about what an identity is and look at some examples of mathematical identities. So, in my last video, I mentioned that an identity is a mathematical statement that is true for all numbers, and that is almost the correct definition. That is almost a precise and true statement. So, to be a little bit more technical, mathematical statement that is true for all values within specified domains, that is an identity. So here's an example. This equation x plus 2 equals x squared minus x minus 6 all over x minus 3. This statement is an identity. So check out what I've done here. I'm thinking of sort of each side of this equation as a function. So I'm thinking to myself, for all the values of x that I could pick, x plus 2 will give me sort of various outputs. And this function, if I graph this function, that's just a line with a slope of 1, a y-intercept of 2, pretty basic function. And then this function over here looks much more complicated, but that function too is a line, except there is a removable discontinuity at x equals 3. The point 3 comma 5 on this function right here is a hole. So I've got some of the calculator screenshots here to sort of assist us to how we could think about sort of each side of this statement being a function. And then we could sort of verify, that these two mathematical objects really are the same for the most part. Like they're both producing this graph that looks like it's a line. And then when we look in the tables are identical except the 0.35 would be on the line y equals x plus 2, whereas 3,5 is a hole on the function y equals x squared minus x minus 6 over x minus 3. So other than taking x to be 3, for all other real and complex, for that matter, values of x, this is a true statement. So if someone just presented us with this statement, how would we go about proving that this statement is an identity? Well, sort of the strategy here is that we want to simplify one of the sides to look like the other side. So this is really we're going to be using simplification techniques. It's a lot of substitution and algebra and mathematical manipulation here. So probably the most common method is people would probably pick this side and just sort of isolate this expression and make this expression look identical to x plus 2. So this will not be very hard to do. We could factor this expression. And then this factor of x minus 3 cancels, and look at that. We wind up with x plus 2. So if I just fill down both either side here, that's sort of what my proof would look like for proving that this statement is an identity. So notice I'm not really doing anything to the left-hand side. I'm just sort of manipulating the right-hand side to make it look like the left-hand side. So I'm not like solving the equation here. I'm almost thinking about this statement as having like a question mark over this, over the equal sign, where it's like, are these two mathematical objects really the same? Question mark. That's sort of what I'm trying to establish here. And through manipulation here, I've shown that the right-hand side really does equal x plus 2. So this original statement is really just saying x plus 2 equals x plus 2, just the right-hand side was a little bit in disguise. Now notice, is the right-hand side exactly x plus 2? Well, I mean, for the statement x plus 2, x could be 3, but in the right-hand side, x can't be 3. So when I say these two things are identically the same, I mean, I'm really saying they're identically the same if I'm only looking at the domain of sort of each of them, looking in the domains of each of them in the original problem statement. So I'm looking at all real numbers except for 3. And these two things are identically the same. Sort of, I could have taken a different approach here, though. This wasn't the only way to show that these two objects were the same. So let me just erase my previous work here. So one sort of thing I could have done here is I could have said, well, you know what, I'm going to take the right-hand side, and I'm going to multiply the right-hand side by x minus 3 over x minus 3. Perfectly allowable, because x minus 3 over x minus 3 is 1, and if I multiply x plus 2 by 1, that really just gives me x plus 2. So it's like I multiply by 1, I'm not changing what x plus 2 is, but I might make it look a little different. So now if I sort of multiply out my numerator here, I'm sure we can see what's going to happen before I do it. Look at what I wind up with. I wind up with exactly the right-hand side, and then I could just, sort of to make this look really nice, just copy down the right-hand side. And so I've taken a different route to show that these two mathematical objects, these two expressions, they're exactly the same. I've sort of manipulated the left-hand side and showed that it does, in fact, indeed equal the right-hand side. So sort of there's a bunch of different techniques and ways, and a lot of these proving that a statement is an identity is sort of personal preference. So I really enjoy doing these in class because a lot of times we can have some awesome discussions, and people have really clever ways to show that two expressions are indeed identically the same. So just a quick talking point here. If an equation has infinite solutions, that does not imply that the statement is an identity. So here's sort of my favorite example, sort of the equation sine of theta equals cosine of theta. So this statement is clearly not an identity. The sine function, sine of theta, is not exactly the same function as cosine of theta. Now, this equation does have solutions. I mean, if theta is pi over 4, the sine of pi over 4 and the cosine of pi over 4 is both root 2 over 2. So if theta is pi over 4, that's a solution to this equation. And if I add any integer multiple of pi to pi over 4, all of those infinite solutions are solutions to the equation. So for example, what would another one be like? 9, the sine of 9 pi over 4 would be root 2 over 2. The cosine of 9 pi over 4 would be root 2 over 2, et cetera, et cetera. And also, I believe that if theta is 5 pi over 4, yeah, the sine of 5 pi over 4 is negative root 2 over 2, and the same with the cosine of 5 pi over 4. And again, if I tack on any integer multiple of 2 pi to 5 pi over 4, that produces another solution to this equation. So this equation has an infinite number of solutions, and if you think about the graphs of the sine and the cosine functions, which I showed the sketch of here, so there's pi over 4 right there. That's a solution to the equation. There's 5 pi over 4. That's another solution to the equation. There's, what's this right here? That would be like maybe negative, what would that be? That'd be like negative 3 pi over 4 is a solution to the equation. Great. So you can see that the graph of the sine function and the cosine function, there's an infinite number of intersection points. In each of the values of theta at those intersection points provides a solution to this equation. So there's an infinite number of solutions, but that equation is not an identity because the sine, for example, the sine of 0 is 0, the cosine of 0 is 1. So this is not a true statement for all values of theta that are in the domain of both the left-hand side and the right-hand side. So I just wanted to point that out because some people get confused and they start thinking when you talk about identities that any equation that has an infinite number of solutions is an identity. But that's definitely not the case, and this sine of theta equals cosine of theta is a good equation to sort of demonstrate that. So now let's look at a sort of classic example that comes up in a lot of texts. So this statement is an identity, and we want to prove that it's an identity. Great. So I'm going to take the right-hand side here. I'm just going to sort of simplify the right-hand side, and I'm going to make the right-hand side look like the left-hand side. So now I'm going to multiply the right-hand side by 1. But see, if I multiplied
the right-hand side by 1 over 1, that's not very interesting, because I would just get sine of theta over 1 plus cosine of theta, but that's what I'm looking at there. So I want to multiply by 1, but in sort of a clever way, so that 1, but I'm going to multiply by sort of this version of 1 minus cosine theta over 1 minus cosine theta. So first notice that 1 minus cosine theta over 1 minus cosine theta is 1, so I'm multiplying by 1, so I'm not changing the right-hand side of the equation. But now why did I choose sort of this version of 1? Because 1 minus cosine theta is the conjugate of 1 plus cosine of theta. So sort of one technique or sort of point of trickery that I've picked up from doing a lot of these problems is that multiplying by a version of 1 that involves the conjugate of one of the denominators often produces a desirable result. So I picked this example because I sort of used a technique that you might not think of the first time you see this problem. Once you've sort of seen this technique once and you start applying it, then you'll see in the future that it becomes a little bit more of an obvious thing to do. So if I multiply the denominator, the 1 plus cosine of theta times 1 minus cosine of theta, I get 1 minus cosine squared theta. This, of course, equals, I'm just going to keep the left-hand side exactly the same. Not going to do anything over there. Now, 1 minus cosine squared theta, that I can make a substitution using one of my Pythagorean identities. So if I remember back a few videos ago, we proved that the sine squared of theta plus the cosine squared of theta always equals 1 for all values of theta. That statement is an identity. So since I know that that statement is true for all values of theta, I can start using sort of variations on this theme when I'm proving other identities. So now if I look at this, if sine squared theta plus cosine squared theta always equals 1, then 1 minus cosine squared theta equals sine squared theta. So I'm going to make a substitution here. So I'm just going to copy down the numerator again, but in the denominator I'm going to replace 1 minus cosine squared theta with sine squared theta. And we can see here that I've completed my proof, because this sine of theta would cancel with one of these sine of thetas in the denominator. And look what I'm left with, 1 minus cosine of theta over the sine of theta on the right-hand side, but that's exactly what my left-hand side is, meaning that this statement this original statement I started with was indeed an identity. And I have sort of shown that. So again, I picked that example because the technique there of multiplying by a version of 1 involving the conjugate, that's sort of not always an obvious thing to do, sort of when you're sort of new to looking at different identities and working with trig functions, but it's sort of a great technique to sort of have in your proverbial toolkit. So good luck with proving identities, and we're going to have a lot of fun with these in class.